Color palettes in professional films are often adjusted by skilled colorists through a color grading process that is difficult for amateurs to reproduce. We present a new method for color grading that transfers the color palette of a model video clip to a user's video sequence. For example, this input sequence can be made more dramatic using a teal and orange color scheme extracted from the Transformers movie shown on the top right. Color transfer has been studied for images, but extending it to videos is not easy. Applying a color transfer independently to every frame of a video can lead to temporal inconsistencies. For instance, a man passing behind this main character brightens the background. Conversely, computing a color transformation for a single pair of frames and applying it to every frame leads to color drift as the lighting, exposure, and white balance suddenly change. Instead, we propose a technique that lies between these two extreme cases. We compute per-frame color transformations and filter them to ensure that the resulting transformations are temporally coherent when applied to the input video. We proceed in two stages. We first compute the color transformations for each frame of the input video to a set of representative frames of the model sequence. Our goal is then to filter these transformations to avoid abrupt changes that occur during short events while appropriately placing keyframes. We perform this step with a novel curvature flow technique. Given a pair of input and model frames, our first step computes a color transformation that brings the input image to its desired appearance. We decouple our processing of the luminance and chrominance of the image. We transfer the luminance with a regularized 1D histogram matching technique and chrominance using a set of affine transformations computed for shadows, midtones, and highlights. Please see the paper for further details. We can also handle spatially varying color grades by computing the transformations for each segment of a user-provided binary segmentation, which is transferred to an alpha matte and further temporally smoothed. All results in this video use user-specified mattes. Although we are now able to transfer the colors of a particular frame of the model to a frame of the input video, the question arises of the choice of this model frame. For example, transferring the colors of this outlier frame from the Dark Knight movie to this reenactment produces an unexpected result. Our technique first automatically clusters the model video into a small set of representative model frames. We thus restrict the processing to a small set of model frames. This also reduces the chance that a bad model frame is automatically chosen for color transfer. For each frame of the input movie, we then select the closest representative model frame in appearance and estimate the color transformations that match the colors in these frames. For instance, the first part of this reenactment in shadows has been automatically matched to the darkest representative model frame, while the second part has been matched to a representative model frame in the light. As we have seen, treating frames independently results in artifacts. Instead, we propose a novel temporal smoothing scheme that considers our set of transformations as a curve in a high-dimensional space. Regions of this curve with a high curvature correspond exactly to instants in the video with temporal artifacts. Based on this observation, we design a new smoothing technique akin to curvature flow that places keyframes in regions of low curvature and performs a geodesic interpolation in between. We derive formulas for curvature in a principled mass transportation framework. We display our curvature estimation in red. Keyframes, marked with blue crosses, avoid instants where the scene changes abruptly. In this sequence, we compared our method to Pittier and Cochrane's global affine transfer model applied per frame, matching a hand-picked model frame. Our model better captures the orange skin tones and stabilizes the face color over time. This allows us to produce temporally coherent color grading that we now demonstrate on a few examples. Please see the additional materials for more results.